Okay, everyone, so I just want to make sure that everybody knows each week to look on the calendar here and see what's due. We have most of it set up for the entire semester, but sometimes things change, so it's always useful to check it out. So right now, you see you have homework due tomorrow, and the Wednesday homework generally is pretty short because you don't have long to do it. It covers the lecture from the day before. So because why do I do this? Because on Tuesday I want to make sure that you know what we're talking about for the next lecture. So for Thursday's lecture, etc., I want you to have already done the homework for it, etc. So I've just found that doing short homeworks, multiple short homeworks, helps people learn a whole lot better than doing more intermittent, longer homeworks. Remember back in high school, you probably had homework due every night, and people really seem to learn a lot better that way, to have short quizzes, short homeworks, etc. So because it's computer graded, we don't have to use, it's easy for it to be graded. So it's easy for you to do because you get feedback right away, and that's the best way to learn. But it's short, so don't worry. People say, I won't have enough time to do it. This Wednesday homework is really short, and it covers the previous lecture. So right now, too, there's this bonus part 2, and that's due Friday. And it would be a good idea to look at it before next lecture because it's really it's a preview of what we're talking about in part 2. Okay, which is what we're going to start on Thursday. Now, what else? Let's see. So I want to look at this Lon Kappa right now, and you have homework 1 and homework 2 is posted. You've already done, once a homework is completed, you can practice it again if you want. This is useful for to practice if you got something wrong. So you can go in here and do the homework over again, and it's ungraded. So let's say you missed a homework because you're joining this class late. You get to drop 3 homeworks, but you should definitely always go to the practice homework and make sure you know how to do it. We'll also be putting practice tests up as well. So these, so you get when it's a problem. For most of the problems, you'll get different numbers because for calculated problems, everybody gets a different number. So when you do these practice homeworks, you get new randomizations. So it's not like practicing with the same numbers over and over again. You get a new randomization each time. Any questions on that? All right, and so let's go back to, there's also, I guess that's all that's up here right now. There's also going to be bonus R exercises, and those are I strongly encourage everybody to do them. They're just doing the same type of thing we do in class, but using R. So for those of you who aren't taking the R independent study, which is most of you, this is a good introduction to R. And the first one is due, I haven't posted it yet, but the first one is due on Friday, February 2nd. And you'll have 5 of them. All right, so any other questions? And office hours are every day, 4 to 6 p.m. Stop by if you have any questions whatsoever. TAs, I won't be there today, but I'm there almost every day. Just today I can't. But there'll be TAs there that can help you. All right, so let's go back to the document camera and finish up part 1 on type 1 and type 2 errors. So, all right, so this is just like the homework that you did in homework 1. Let's just focus this a little bit here. And we're going to extend this problem on the next page and look at what if the alternative hypothesis here was a 2-sided hypothesis instead of this 1-sided hypothesis here. So let's just turn the page here. And now we're on page 10. And we're just going to be doing the same thing and calculating a type 2 error we're calculating beta. That's the probability of making that type 2 error. And we're going to be calculating it now for a two-sided instead of a one-sided alternative. Okay, so when we set this alpha, the probability of a type 1 error, to a particular value, and let's say it was 5%, that's the convention, then we're setting that probability of a type 1 error at 5%. Now for a two-tailed test, what does that mean? That means that that 5% is now distributed between two tails instead of one. So what that's going to do is change the Z alpha. Here, let's go down here and see what that means. Okay, so let's say we want to find, let's look at the difference here. So for a one-tail test versus a two-tail test, or two-sided test. Okay, so we've been doing these one-tail tests, and so when we set, for a one-tail test, if we set alpha equal to 5%, that means that when the null is true, when this null is true, you have some distribution here, and we're going to be rejecting the null at 5%. So for a one-tail test, this right here, this is what we've been doing so far, is 5%, right? This right here is 5%. And then we've been figuring out what this z-score is corresponding to 5%. Okay, so that's like the critical value of z corresponding to 5% for a one-tailed test. We've been calling it this z alpha. And then we said, how do we figure that out? Well, we draw it so that there's 5% here as well. And then just because we're using the table at the back of the book, we're looking up the middle area of 90%. And we saw that this corresponds to 1.65 or 1.645. And between 1.65 and negative 1.65, 90% of the area lies. And so what we're saying, when the null is true, if we put our decision maker here, the null cutoff here to reject the null, then 5% of the time when the null is true, we're going to be wrong. And that's the type 1 error, but it's all lumped into one side. Because our alternative is that we think that this isn't the true value is really on this side. If we thought let's say we're testing a drug and we think the drug works better, cures more people, then we know which direction it's going in. But let's say we don't know. Let's say we're comparing, we're testing a drug and we don't know it's a new drug. We don't know if it's good. Let's say it might work worse than the old drug. We know it's different. It's doing a different mechanism, like it's working by a different mechanism. We expect it to be different, but it might be worse. So we don't want to do a one-tail test. We would want to do a two-tail test because we're not sure. We think it's different, but we're not sure in which direction. Is it better or worse? And that happens a lot. And then you do what's called a two-tail test. So then that same 5% is now distributed between two tails. So when the null is true, we're going to say, what's the probability of getting this 5% distributed in two tails? So then it would be, we'd have to go further out, have 2.5% on either side, right? So we don't know whether it's going to land in this direction or this direction. So our alternative is just, we're not sure which way it will go. It's a non-directional alternative. And so now we have this 5% distributed between two tails, which means that the z-score, how far, excuse me, let me just make this go out wider. So what it means is that how far we have to go out on this curve before we'll reject the null is further. And then you'll have 95% in the middle. And between z, then your z alpha would be 2. the critical value to reject the null would be 2, or more accurately, 1.96. So between 2 and -2, or -1.96, 95% of the area lies. So in other words, you have more uncertainty. You don't know which direction your alternative, you know it's different, but you don't know whether it's better or worse. So you actually need more evidence to reject the null. You have to get further out to reject the null. It's really equivalent to lowering your type 1 error from 5% to half of that, 2.5%. So that's the idea. Any questions on that? And very often, the default in most software programs is for a two-tailed test. Just basically because I think that really often people want to set that type 1 error lower, really setting it 2.5% instead of 5%. That's what it in effect does. Okay, so let's write this. So let's fill this in now. So now instead of, so for a two-tailed test, that means 5% is now distributed between two tails instead of one. So the middle area is 95%, which corresponds to the z alpha equal to approximately 2. For using the back of the table, I'll just show you here, because this was the table, the back of the book table, because this is the one that will be on your exams. This is your only resource on the exams for the normal curve, so I just want to make sure everybody knows how to use it. So here, if you were doing a two-tailed test, you would have 95% in the middle. So it's approximately 2. I mean, it's actually between 94.8 and 95.45. If it's more accurately 1.96. So people just often round to 2. They always say between, 2 sigma. They just round to that. But if you want it to be more accurate, it's 1.96. Okay? So on the homework, sometimes I'll ask you to be more accurate and use 1.96. Let's write that down. So it's approximately 2, more accurately 1.96, instead of the 1.65. Does this make sense to everybody? All right. So then once the alpha is set, then once you set that type 1 error, then the type 2 error is always one-sided, because the evidence is going to land one side or the other. So for two-sided, if your hypothesis is two-sided, you want basically what you're going to do is just set a different z alpha, and then you'll have a smaller type 1 error, and then your type 2 error is just going to get bigger for a given standard error. Okay, so let's calculate the probability of a type 2 error. In the example before, when the alternative is two-sided. So we'd perform, remember what this is, so let's go back and look at the example. So if we were going to change it, so the professor claims that the students are only spending 6 hours on the homework, right, with a standard deviation of 4, and we think, the class thinks it's more than that. It's really 8 hours. There are people they know are spending a lot more time on it, and so that was the alternative. And that makes sense to do one-sided. What would a two-sided even look like in this case? It would look like, it really doesn't make sense in this case. It would be if you thought this 6 hours was wrong, you just think it's significantly more or significantly less. So it doesn't make sense in this case, but let's just go through the mechanics anyway, because often that's what the default is, and just so you can see what's going on. All right, so we'd perform it if we thought the true class average was far away from what the professor claimed, but we weren't sure in which direction. We weren't sure whether it was more than, 2 hours in one direction, or less, more than 8 hours, or less than 4 hours. That doesn't really make sense here, but let's do the calculation anyway so we can see how it works. Questions? It actually really makes sense in the motivating example that we've been using, the experiment that's going on right now in this class, the study that's going on. I'm using a two-sided because I don't know which method works better, whether it's the in-person class or the online. We really don't know. We hope they work about the same. So this is a rare case where we're hoping to show that the null is true, that they work about the same. because then it would just be wonderful. People could just decide, just on the, if they work equally well, then we could open up every class this way. Wouldn't that be great? All your classes could be filmed, and you could just arrange your schedule however you want, and it really wouldn't, you could just watch the lectures at home or go to class just according to your preference. It would be better it would save a lot of money, and it would be great for you guys. So we're really hoping that there isn't much of a difference. But that's unusual. But it's two-sided because we really don't know which is better. Okay, that's the idea. So let's just do it in this case. So what would be, so here we have our usual. Let's just copy everything from before. We thought the null was that it was, the professor claims it's 6 hours. So this is as hours, right? And then as a z-score, we have 0 here. So this is our z-axis. And then we already figured out that the distance from the previous, on the previous page, we figured out the standard error, right? We don't have to write this all over again because I just want to show you what's different. We still have this, 4 is the standard error. We're figuring out the standard error first. That's 4 hours over the square root of n. So that's what we got, right? And then we still get this same distance here. As a z-score, we know the distance between 6 and 8 is 2. And as a z-score, how many standard errors is that basically? Well, that's 2.5 standard errors, right? That's 2.5 standard errors. And now all we're doing here is adjusting this decision maker. Instead of having it at 1.65, what are we doing? We're shifting it to 2. So that, as you can see, if we shifted it to 2, it goes all the way up to here. That means we're lowering this yellow region, the type 1 error. We're lowering it from 5% here to 2.5%, and that's going to increase our type 2 error. And so we'll just figure out what that is. So that's super easy, right? Instead of having, so we'll get z beta here. Instead of this, z alpha, instead of now, z alpha is not 1.65, it's going to be 2, right? Isn't that what we just said? We're going to have to change this type 1 error to 5% here, which corresponds to z alpha of 2, or 1.96. So we'll have 1.96 here. And that right there, then z beta will be what? 0.5 or 0.54, depending on how accurate we want to be. And we're going to have more type 2 error. Does that make sense? Everything's the same. It's just when you change to a two-sided, and this is why journals want to do two-sided, basically. Because once you see the data, right, once you look at the data, you know whether it's one-sided or two-sided, depending, like after I examine all the data, I'll know if there's a difference, which direction it goes in. Is the online better or the in-class better? I'll know that. When you start off the experiment, you don't. So they're just very, very worried about people peeking at the data and then deciding, oh, well, now I know which it is. So now I'm going to, so they don't want you to do that, right? So basically they're just lowering the possibility of a false claim it's for political reasons, basically. What else can I say? Why do they always, all the default is two-sided? It means basically people are asking you to have a type 1 error of 2.5% instead of 5% to protect against dishonesty. That's all. Okay, so you're going to see this all the time, the two-sided. So basically it's the same as changing it to, why don't I show you, just like on the, before we even do it, I'll show you on the data program here. So let's go back to the PC. And here, I can show you right here. Why don't we try it? Okay, so let's go to our power calculation, right? And what are we going to do here? Our null is 6 hours that they spent on the homework. And our alternative, we think we're spending a lot more, that the students are spending a lot more, so we say it's 8. And then the standard deviation was 4. That's what the professor claimed. It was 6 hours, a standard deviation of 4. And now it's going to look like, and the sample size was 25. So if you look at your notebook, this is what we got. We have the sample size, we have the distance is 2.5, right? There's our standard error of 0.8. So how did we get that distance? We said 8 minus 6 is 2 divided by 0.8, and we got that 2.5, right? And so from here to here is 2.5, and then when we set the 5%, we said that Z alpha is 1.65. Here it's more accurate, 1.645. So then 1.65 plus 0.85, this distance from here to here, this whole thing is 2.5, right? So 1.65 plus 0.85, or 0.8, they're doing a little more accurately, is 2.5. As an absolute value, as a distance. Here it's negative because it's to the left on the null curve. All right, and so then what did we do? So then we figured out, okay, so this is 5%, and then between negative 0.85 and positive 0.85, when you look at your notes, we had 60% in the middle, so that leaves 20% for each tail. That's what we got here. A little bit more accurate, 19.6. So now we can change it to a two-sided test, and what's that going to do? You see what it does? Now we have a Z beta of 1.96. So 1.96 plus 0.54 is 2.5. So now you're going to look up the, you're trying to find, so in between, you're going to have a smaller middle area and a bigger left-hand tail here. The left-hand tail is what? About 70%. And beta is about 29.5%. You could also, instead of just clicking there, you'll get the same result if you change the type 1 error to what? Not 5%, but what? Half of that. So we'll change it to 2.5, and we get the same exact result. That's all you're doing. When you're doing when you say you're doing a two-sided test, you're just taking that type 1 error and changing it, cutting it in half. That's all you're doing. And of course, then your type 2 error for a fixed sample size, for fixed standard error, when we change this type 1 error, there's a zero-sum relationship. They have to add up to we're just dividing that distance of 2.5 into two pieces. And the smaller we make the red part, which is the type 1 error, you think, oh, you want to make that smaller, well, that increases your type 2 error. And that's all that we're doing here. Okay? So any questions? So let's just do this calculation and see if we get the same answer here. So let's go back to the document camera and do it. Okay, so everything is the same here. Now that you see this, we can just say that everything's the same as before. So we can just write it down here just so I have more room. Let's just see, what are we doing? So everything is same as before. So ZD is still 2.5, same as before, nothing's changed there, right? And now ZD, we know, is divided into two pieces, Z alpha and Z beta, and their distances, so let's just make them absolute value. So now, for a two-tailed test, Z alpha is no longer 1.65. It's what? 1.96. Do you want to match it up exactly? We can match it up exactly with there. So we'll say that's 1.96. So we know this is 2.5. So 1.96 plus, so this must be 0.54 as an absolute value. That's all we're doing. And then we're saying, okay, so now we know that's Z beta. So now we're just focusing on the alternative part, that left-hand tail. And that 8 hours is, think of it as 0, right, as a z-score. And we're going this direction, 0.54. So between negative 0.54 and positive 0.54 is what? So let's just look that up in the back of the book. So this is between 0.54 and negative 0.54. We're just trying to get that tail there. So let's look it up in the back, and we say between 0.54 is what? So 0.54, that's about, it's 41.77. So we could just say 41, I don't know, can we just, let's just round that to 42 so we can do it quickly in our heads. So we'll just say that's 42% here, 42% in the middle. So that means that that's 58, so that's 29% on either side. So that blue region, I guess they came up with, what, 29.5, because they didn't round to 42. Okay, so let's just look at it, and it looks like this. That's what we did. So that's super easy. And so then what's our power? Our power is just going to be 71%. The power is all this part. So this is beta, so that now you have beta equals 29%. The probability of a type, why did I just ran out of ink? Darn. So beta equals 29%. So the power, this is beta, just this blue part. And then the power is the rest of the curve. The power to detect a difference that's really there. So the power, we'll just draw it like that, is just 100% minus beta, which is equal to 71%. All right, so why don't we draw it up here just so you can, this curve up here, just so you can make sure the picture's right. So what we had was like, all right, so here was the null, right? And we have to draw, and we said that the standard error was 0.8, so this would be 6.8, 7.6, and that's 8.4, and our 8 of our is right there. 8 is 2.5 standard errors. 2.5 standard errors, right? And so that's where the top right here of our next curve is. And it's going to have the same distribution, so let's just draw it like that, right? And so what do we have here? Basically, we have this, we have 6 and 8 in terms of hours, but in terms of z-scores, what is this whole distance there? That's a distance of 2.5, right? The whole thing is 2.5. From here to here is 2.5. So now instead of, now we divide that up with our, into two pieces, that 2.5. Right? We're dividing it up into two pieces. And if we only want 2.5% in this little tail, then we have to make it go out further, almost all the way out to 2 standard errors, all the way out to here. 2 standard, it's 1.96, right? All the way out to about 2 standard errors. That's 1, that's 2, and that's 2.5, right? So now we have this littler alpha. So even though alpha is equal to 5%, we're still doing that. Alpha, we're looking for z alpha is equal to, is the critical value that corresponds to 95% in the mirror. Z alpha corresponds to the z-score that will give you 2.5% in each tail, to 95% in the middle. And so now that's little part there is 5%, right? That's, I mean, it's 2.5%. So this little part right there is equal to 2.5%. There's another 2.5% over here. If you wanted to be super, super careful, you'd go out here to another, like let's say it landed on the other side. Well, then once you'd probably, if you want to be super, super careful, this goes to infinity, right? So theoretically, you could also count in that tiny little percent if it, nobody does that. Let's not even think about it. This is why it's always the alternative, the z beta is always one-sided. All right, so that's 2.5%. And now, what is beta? beta is this blue part here. And what's that going to be? Well, let's draw it first. It's this part right here. It's all that. And that's going to be, that's beta, and that's going to be, well, let's get the, okay, so this part right here, that right there is, if this right here is 1.96, then that is 0.54, right? And so then this is the z-score, that's z beta, and then this part is going to be what? Got 29%. So the power is all that, and that's 71%. So this is z beta, the absolute value, and this is z alpha. Does that help? It's not hard at all. It's just thinking, okay, you're just making your decision, make your type 1 error smaller so your type 2 error increases. All right, questions? No questions at all? So you got that down? Fine. Can we move on? All right. So now, much more common with these power calculations, what do? They come up when you're designing an experiment. Okay, so what we did so far was for a given sample size, so for a given standard error, for a given level of sampling error, when you set your type 1 error, your type 2 error is determined. And we just figured out how to calculate that, all right? But usually what happens is you have in mind a type 1 and a type 2 error that you want to achieve. And in order for your experiment to be, or to get money for your funded, you're going to have to say, okay, I'm going to do it with a type 1 error of usually under 5%, and then a type 2 error of under 20% about. They want a power to achieve, to detect a particular effect size that you're aiming for with 80% of the time. So how do you do that then? Basically, if your type 1 and type 2 errors are set, think about it. If your type 1 and type 2 errors are set, that means your distance here is set both as a z-score and as an effect size. So you're planning this experiment, you say you want to see this big an effect, and these, you're basically saying how much error on each side you want. And then what you're trying to do with the standard error is saying, how narrow do I have to make my curves? How precise do I have to make my curves? And that's what you're doing with the sample size. How big a sample will give me the precision I need to achieve that, to only get that type 1, get that type 1 and type 2 error, and for the effect size I want to see, just how much precision do I need? How narrow do I have to make my curves? Right? So that's the idea. So in the previous examples, you were given the sample size and asked to calculate the type 2 error. But in planning a study, you'll need to calculate how big a sample you'll need to detect the effect size you're looking for at set levels of alpha and beta, right? So most grading agencies request that you plan your studies with alpha less than or equal to 5%, usually for, well, it depends. Let's just say sometimes for type 1 or depending on if you want it one-sided or two-sided, that's going to affect things, right? But it's 5%. And beta less than 20%, which means a power greater than or equal to 80%. In other words, you need to find the smallest n, the smallest sample that will detect an effect at least as big as the one you specify in your alternative, given the type 1 and type 2 error limits conventionally set. That's what we're going to do here. So how should you choose that alternative? Like the effect size, well, that, as we discussed earlier, that depends on the difference you care about. You want the minimum difference that's important to you. You want to detect a small difference if it's important. Big differences are easy to detect. You want to detect the smallest difference that's important to you. All right, so like on the previous page, let's just do the example. Let's say how big a sample would we need if we wanted to achieve 90% power? Okay, what did we achieve? Let's just do the one-sided to keep it simple. How much power did we get here? We got 80%. When we changed it to two-sided, we got less, of course. Now, let's say we wanted 90% for the one-sided. So we just want to figure out how big a sample we need to do that. That's all we're going to do here. All right. So if we want 90% power, how are you going to find, what is that? Well, then your type 2 error is what? 90% power means they have to add up to 100, right? So this has to be 10%. So beta is 10%. Basically, okay, so you want 90% power. So in power, when you're doing these, it's always this is for the alternative curve, and that's always going to be one-sided. So let's say it's 90% power, so we want all this from here on in to be 90%. So that means this part has to be 10%. So then what z-score corresponds to that? Because what z-score corresponds to that? So we have to look that up. And so let's look it up. And so if we have 10% on one side, to use this chart, we'll have 10% on the other side, and then what will be in the middle? 80%. So we look at 80% here, and let's just, 80% is going to be a little bit less than 1.3. Let's just round to 1.3. All right, so let's do that. So we have to have 10% on the other side. So this is 10%, that's 10%, so that's 80%. So we just are looking up the z-score corresponding to a middle area of 80%. And we saw that the z-score is what? This is between 1.3 and negative 1.3. So that's the critical value corresponding to 10% in that tail, the critical value of z. So that's 1.3. We just want it as a distance. Because all we're doing here is saying, okay, we still want to detect that 2 hours, at least 2 hours. We think people might be spending more than that. You know, some of us are spending a lot more than that in the class on homework. But we want to detect at least the 2 hour difference, so that's the 8 minus 6 here. And now the z alpha is still 1.65. Let's keep it the one-sided test. It makes total sense in this case. And now z beta we want to be 1.3, right? So we have that. This is z alpha, and this is z beta. And then what we're trying to see here is just what standard error will achieve that. How narrow do we have to make the curves to achieve this, right? So remember what the standard error is. What is the standard error? It's the sigma over root n. So we can just rewrite this as, right, as 2 equals 2.95 times the standard deviation, which was what? 4 over the square root of n. And then we can just solve for n. And that will tell us how big a sample size we need to achieve this. That's all we're doing here. Right? So we can just say the square root of n is equal to 2.95 times 4 over 2, which is equal to 5.9. So then n is equal to 5.9 squared, which is 34.81. And generally you round up to the, you don't have 34.81 people, so you'll round up to the highest integer, to the nearest, round up to the You round up. Even if it was 34.2, you'd round up. So you round up to nearest integer. So it would be, the answer would be 35. How's that? Any questions on that? So how would it change? I mean, do we want to do this with the two-sided? Right away, you're going to know with the two-sided, basically what's going to happen is what? This 1.65 is going to change. It's going to get bigger, so we're going to need a bigger, we're going to need, the type 1 error is going to be, we're going to need a bigger sample size, right? If we do repeat with the two-sided. Should we repeat with the two-sided? Do you want to do it? We can do it. It's going to be, what's going to change? This 8.6 is still the same. 8 minus 6, excuse me. We still want to detect an effect size of 2 hours, right? But, and now what's going to change? We still want 90% power, so the 1.3 is going to stay the same. But with the two-sided, this 1.65 is going to change to approximately 2. To have, 95% in the middle will be a z-score of approximately 2. We could say 1.96. Let's just do it in our heads with 2. So that would be 2 plus 1.33. And the rest is going to be the same, times 4 over the square root of n, right? So now when we solve, what do we get? So now we just get the square root of n is going to be equal to, instead of the 2.95 here, it's going to just be 3.3, right? 3.3 times 4 over 2. The only thing that's going to change is that. So that's just going to be bigger, right? So that's going to be, what? 6.6? 3.3 times 2. And so then n will equal 6.6 squared, which is equal to 43.56, and then you'd round up to 44. So you need more people. It's just harder. Look, when you have two-sided, think of it this way, when you have two-sided, you have more uncertainty. So you have more uncertainty means you're going to have to get more evidence to reject the null. You're going to have to have a bigger sample size. That's all. Yeah.
So if we can pick alpha, why are we doing the two-sided thing? Like, we don't actually care about the
Exactly. Exactly. Good question. If we can pick alpha, why are we even doing the two-sided versus? Because let's say you really believe that you only want 5% error. Like you're taking this really sincerely and you're not trying to satisfy some condition. Well, then you're thinking, I just want to, then you would think, what's, 5% error, if you have this uncertainty, would translate, it would depend on your situation, how much you knew. I mean, if you really believe this, okay, I want 5% of the time, I want to, is what I want to reject the null when the null is really true, to have a false alarm, right? And if you really think that's about what you want to risk, well, then it really depends on whether it's one-sided or two-sided. So the first time through, you might do an experiment like where you need more evidence. You'd say it's two-sided, like what's going on right now. I don't know whether the online or the in-person is a better method. So I need more evidence to begin with. But let's say after I finish this, look at the outcomes and everything, then I realize, let's say I realize one really is significantly better than the other. Then the next time I did the experiment, if I wanted to repeat it, I would have a one-sided. And I wouldn't need as much evidence if I put all one-sided in the 5%. You see what I mean? I mean, that's the way you really should do science. Rather than just, but if somebody says to you, 5% no matter, and it's always going to be two-sided, then basically it's like having a type 1 error of 2.5%. I don't know if I'm, does that make sense to you?
I mean, in an example like the ongoing experiment, yes. In this scenario, no. But in the ongoing
Yes. But so often it's like these rules get made. This is because we live in a society where people make rules, right? Lots of times there's these black and white rules, and sometimes it's like, okay, 5% is what you need to get it accepted in a journal. So essentially what they're saying is they want 2.5%. Because they're not really paying it, you know what I mean? Yeah. But good question. But really, when you're doing something and you really, really care about solving the problem, you do think about the one-sided and the two-sided, and you think about what you want. Whether you, so I really, and in so many contexts, that 5% doesn't make any sense. It's just a convention. Any other questions? Yeah. What I prefer to use, I better start repeating these questions, right? It's for everybody to hear. So would you prefer 1.96 or 2? That's a good question. Usually you should use 1.96, but I will tell you which I would, on the homework, I think you usually should use 1.96, just because it's more accurate. But when we're doing things in our head a lot, it's just easier to just use the 2. And I think on the homework problems, I'll specify like which to use. Any other questions? On exams, I usually, because you have that, I usually just let you use 2, and I'll say that. Okay? Hey, I have a question to ask you. Would you prefer if I use 1.96 or 2 when we're doing these questions together? 2? Should we do that as an iClicker? I didn't set up the iClickers, but we could try the, we're going to start iClickers next time. Just raise your hand. Would you prefer when we're doing these together? Do you want me to just do 2? Use 2? Raise your hand. Raise your hand if you prefer I use 1.96 when we're doing it together. Wow, it's pretty even. It's pretty, what I'll do is probably, if it seems like it matters, like I want to match it up to the program or something, then I'll do it. Otherwise, I'll probably use 2, because the 2 won. People want me to use 2. That was the majority. We can do it again as an iClicker question. All right. Any other questions before we look at the next problem? What is the next problem? We're moving along pretty quickly here. Whoa, we're almost done here. We just have this one problem left. So you're going to get out early. Okay. Great. Okay, so now, two sample z-tests are much more common than one sample z-test. We often want to know if 2 groups differ or whether a treatment works better than a control. So if we're designing a study or an experiment comparing 2 groups, and we want to do these power calculations, we're going to use it's the same idea, but the only thing that changes is the standard error formula. So we're going to have to use a standard error formula where sampling is for the difference of 2 group averages or percents. We're going to have to use basically the formula that's the variance sum, so the standard error from 2 sources. Okay, so let's say if you have 2 sources of variation, if you're if you're randomly assigning people to treatment and control, and you don't, you're going to have 2 sources of variation, one from the treatment group and one from the control. They'll each have standard errors. And how do you combine them? Well, it's combined as the square root of the sum of their squares. If it was variances, like what I mean is if you square both sides, then the variances add. But we're looking at standard errors here, so it's the square root of the sum of their squares. I don't want to spend this is something we went over a lot in Stat 100, and you've probably seen before. I don't want to get bogged down right now with these calculations, or if you want to see the proof of this, it's at the back of the book. I just want to say just to do, right now we're concentrating on these type 1, type 2, and power calculations. And I just want to show you, since this is so common, how you would do the calculation with this different standard error. So that's what we're concentrating on now. So now our standard error would be coming from two sources. Now, generally speaking, so you have group 1 and group 2, and they each have their own standard deviations and their own sample sizes. But when you're designing an experiment, you can design it any way you want. And the optimal way to minimize your standard error is to have the sample sizes the same. So most everybody sets these ends the same, right? So you don't have two different ends. And and usually the standard deviations are about the same. So let's just go with that for these calculations, because that's generally what's done. And so now, if these are both the same, then the standard, you're just sampling, when you add these up, you just get 2 of the same thing. So when you take the square root, it's the square root of 2 times SD over square root of n. So this n is just the sample size for each group, and this is the standard deviation for each group. Okay? So that's just generally how it's done. And then you, of course, if you want to change it to a percent, if you're doing a problem involving that, you just multiply it by 100. So we can do this. So here's an example where we could use this. And we say, suppose you wanted to test whether a new drug designed to help people quit smoking works better than the old one. All right? So we plan to randomly assign half the subjects to the new drug and half to the old drug. And suppose typically about 50% typically quit using the old drug, but there's going to be sampling variation. It's not like we don't know for sure it's 50%. Like with Talia guessing, we knew it was for sure 50%, right? We don't know. It could be, it varies around there. So there's a 2-sample z-test, as opposed to the other examples where we had a claim and we're sampling 1 sample. Now we have 2 groups of people. We have one getting the new drug and one getting the old drug, and they're both varying. Okay? Okay, so suppose only 50% typically quit using the old drug, and we think the new drug works at least 60% of the time. So we're going to set, the null is that there's no difference between the 2 drugs, and we're going to set 10% as the effect size to detect. We care about that effect size, let's say. Okay? So how big a sample do we need in each group to detect that difference with a power of 80%? So it's basically the same thing. We have this null hypothesis, which the percent, you can just, remember, use the Greek letters for percent. So it would be, the Greek letter would be a rho. You can think of it as a percent for the treatment group minus a percent. That's a rho. For the control group is going to be equal to 0%. That there's no difference between the 2 drugs. No difference. That's your null, right? And the alternative is that these percents, that this difference, it's going to be one-sided because we really think it's improving. We have evidence, we have preliminary evidence that it's improving. We're going to do a one-sided test that this is greater than or equal to 10%. So at least 10%, so we're going to say that we believe that there's at least a 10% difference favoring the new drug. So it's one-directional. So what would we do? So it's basically exactly like before. We're just going to set this up as this effect size, this difference of 10%. We wrote it as HA minus H naught. That's the 10%. That's our distance in actual units. This is like 10% effect size. And that's going to be equal to, what are we trying to do? How big a sample, right? Power, and we're going to use, did we say what alpha? Yep. So here we have the type 1 and 2 errors are going to be set by that, okay? So we know that it's going to be our usual formula that is what? Is just Z alpha. These are just distances. So this is a distance. between our two hypothesized values. This is called the effect size. This is our distance in standard units. And then we have the standard error, which is like our conversion factor, telling you how many standard units in one of these units. Okay, so this is the standard error. And now it's going to be the standard error of the difference. All right? So we're just going to solve for n here. It's the same thing we've been doing. So this is 1.65, right? That corresponds to z alpha. And for z beta, how are we going to get this corresponding to 80%? Do we know how to do that? Do you know how to do that? How would we do that to get that? Let's do it right here. 80%, let's think about it. If we wanted 80% power, now this is always going to be one-sided, so 80%, think about it as dividing this curve into two pieces. This part's 80%, and this part from here on in is 80%, and this part is 20%. Okay, so we just want that z. So on the back of the book, we'd look up, if we're doing it that way, we'd have to have 20% in both tails, 20% and 20%, and then in the middle would be 60%. So we're just looking for that z-score to get this z beta here. We want that z-score corresponding that, to 60%, so we can do that quickly. 60% in the middle, and we have, let's just say 0.85. Okay, it's a little bit less than that, 60%, but for now let's just do 0.85. So this is between, what we're doing here, this is why we do this is negative 0.85, and this is positive 0.85, but we're just caring about that distance. So it's the absolute value, so that's 0.85. Okay? So it's that times some standard error for the difference. And what's that? Well, that's just going to be, we're assuming the same standard deviations and the same sample size, so we'll just say that's what? Going to be the square root of 2 times sigma. And remember, it's like for 50% is going to be 0.5, or 60-40 will also be 0.5. We did this before. So sigma will still be 0.5. We'll say for both of them, over the square root of n. And then if you're doing percents, you'll multiply it by 100. Okay? So now we just solve for n. So we should do that. That adds up to what, 2.5, right? Isn't it? So that's going to be 10 over 2.5 is equal to the square root of 2 times 0.5 over the square root of n times 100, right? So then we'll get the square root of n is equal to the square root of 2 times 0.5 times 100 over 4. And so then, what's n then? So then n is equal to 25 times 12.5 squared, right? I'm squaring just both sides. That's 12. That's 50 over 4. Yep. And so that's the answer. Okay, and this is 312.5. Okay, so that's n, and that's for each group. That's for each group. So, so you'd round for each group. and for each group. So that would be a pretty big experiment. So that's the idea there. So as I say, for each group, so what you'd really have to do is round each group. So round each group to the nearest highest integer to 313. So the total, your total experiment size. So the total size of the experiment of both groups together would be equal to 626. That would be the answer. I didn't include, because it's going to be a short homework, so I didn't include a problem like this on the homework that's due, but I will for Monday, because you'll have time to do it then. So I'll do it. I'll do an interesting problem. I'll add it for Monday that's on this. Any other questions? Any questions at all? So just check out the summary. These summaries are really important. Read these on your own, and that's it for today. Next time we're going to do eye clickers.